So in this video, I'm going to do another demonstration of doing probability calculations for normal distributions. So the average length of human gestation is 40 weeks, and a baby is considered premature if the gestation is less than 37 weeks, or overdue if it's more than 42 weeks. So suppose the length of gestation is normally distributed, and also that 5% of all babies are overdue. So the first thing that we need to figure out based on this information is the standard deviation of the length of gestation. So before we get to that, let's draw ourselves a diagram to kind of help us out. So on the x-axis here, what we're going to have is the thing we're measuring, which is the length of gestation. So that's x. It's telling us that it's normally distributed. So if we plot it, it should look something like this, the bell curve. So we can mark on the mean of our gestation period, which is going to be this 40 weeks. So that is mu. The other key piece of information I can mark on here is we know that 5% of all babies are overdue. And overdue was defined as more than 42 weeks. So if I mark on the diagram 42, what I can deduce from that is this part here is representing the area under the curve for more than 42 weeks, which is equivalent to the probability of the gestation being more than 42 weeks. And here we're told that that probability is 5%, or you can rewrite this as 0.05 in decimal form. So we've got this kind of key piece of information which is going to help us in answering this first question, which is about finding the standard deviation. So how we can get this out is we know the conversion between z-score and x, and in our case, remember, x is gestation length. So if we want standard deviation, we just need to rearrange this equation. So if I multiply this up to the top line and divide the z down, I get that. So now all I need is the x value that I'm interested in, which is going to be this 42 in a moment, mu, which is the mean of 40 that we know, and z. Unfortunately, at the moment, we don't know z. So if I write underneath here the z scale, we know the mean corresponds to 0. What we need to figure out is what this 42 kind of corresponds to in terms of the z scale. And how we can get that is we have the 0.05 area. So if we look up what the kind of cutoff is for an area of 0.05, we're going to get the z-score. So let's go and do that, and I'm going to use the inverse table. So let's scroll over here. So this is the inverse table. We're interested in this bit here being 0.05. So that's going to correspond to this z-score. So 1.6449. Right, so that's the corresponding z-score for that part. So now let's go and substitute all our information in here. So x is the 42, mu is 40, and z is what we've just come out with. And in a calculator, this is 1.216. So that's our standard deviation. Put this in brackets off to the side. Cool. Alright, so the next thing that we need to answer is what is the probability that a baby is born premature? So the definition of that is less than 37 weeks. So let us just quickly draw our diagram again for this new situation. So mu is still 40, but this time we're interested in less than 37. So that's going to be here somewhere, and that's the probability that we need to calculate, that area under the curve. So again, we're going to need to convert this over into z-scores. So I've already agreed that this is equal to 0 when we convert to a z-score. So we just need to figure out what 37 corresponds to. And we have our conversion equation. So subbing in here, 37 minus 40 divided by 1.216 in a calculator, this is about negative 2.47 approximately. I can mark that in here. So now we need to go and figure out this probability in here using the table. So I can write this as the probability of x, our gestation length, being less than 37, or I can write it as z being less than negative 2.47. This is the one though I can look up in a table. Remember though that the table looks at from the mean up until some cutoff point. So I'm going to do a little bit of manipulation. So I know that half of this diagram has an area of 0.5. And so if I work out the area in this little bit and take it away from the 0.5, it's going to leave me with this blue section that I'm interested in. So minus the probability from, in terms of z, 0. Let's do it smallest to the biggest. So from minus 2.47 up to 0. And then if we want to, we can kind of flip this over because we know that our diagram is symmetric. So the probability of that will be the same as this. So we need to look up 2.47 in the table, and we're going to use the regular table for this. So our z-score, 2.47. So this is 2.4, and then we need it with the 7, this one here, the 7 as the second decimal. So it's 0.4932. 0.5 minus, and if we go and put that in a calculator, it's 0.0068, or in a decimal form, it's about 0.68 or 0.7%. So a very, very, very small chance that a baby is going to be born premature. So part C is to find the lower and upper boundaries of the middle 60% of all births. So again, let's start by drawing ourselves a diagram of the situation. So the mean is sitting at 40, and remember our standard deviation here was 1.216. So we want the middle 60%. So we're going to have a lower and an upper cutoff, which I'll call x1 and x2. And what we know is that the area inside all of this has to be equal to that 60% or 0.6. So if we're going to use our inverse table, remember we need the back or the bottom side of our area. So if the whole thing is 0.6, that's going to leave this as being 0.2 and this as being 0.2, because 0.2 plus 0.2 plus 0.6 takes us back up to 1. So we need to go and look up our z-score, okay, for 0.2 area in here. So this is already 0, and that should give us what this kind of what z-score this x2 corresponds to. So let's go look up 0.2 in the table. Alright, so 0.2, that's this one here. So 0.8416 is the z-score we need to drag across. Alright, yep, I should have probably written this in green to keep it consistent. Alright, so that's the z value that corresponds to x2. And then for this one, because it's just going to be the same distance away, but on the negative side, we can just take this value and make it negative. And that's the z-score that's going to correspond to x1. So finally, all we need to do is go through and convert this over, so that rather than having it in terms of this normalized z-score, we have it in terms of actual x's. So our equation, pop it under here. We're going to need to rearrange it for x. And that's what we get for rearranging. So let's go and work out, I'll start with x1. So the z value for x1 is this negative 0.8416 multiplied by the multiplied by the 1.216 for the standard deviation plus the mean, which is 40. So x1 works out to 38.98 weeks approximately. So that's this in here. Alright, so now let's go and get x2. I'm going to reuse this equation. So z this time is positive. Everything else is the same. And when you type that in a calculator, it's about 41.02 weeks. Alright, so what this means is that the middle 60% of observations are going to lie between 38.98 weeks and 41.02 weeks. So that's all there is for this video, and I'll see you in another one.